Hello, hello. We are starting Unit 10. We have two more units to go, and then we're done for this school year, at least in chemistry. So Unit 10 is on liquids and solids. These are collectively known as the condensed phases. Oh, yep. There's the bell telling us we should start. And when we say they're condensed, it means the particles again are they're pushed relatively close together in both solid and liquid state. And so we're specifically avoiding the gases. And so the very last chapter that we'll cover this semester is Unit 11 on gases because they behave just a little bit differently. So getting started, I have if we want to know why solids and liquids behave the way they do, we need to talk about the forces that hold them together. And if we're talking about molecules, they are known as intermolecular forces. Now, Unit 9 was all about intramolecular. Intra is a prefix that means inside. Like if you've ever had an IV, it's a intravenous. And so that's internally into your veins. Intramolecular refers to the forces that hold atoms together in a molecule. So those are the covalent bonds. So here's an intramolecular bond, and here's an intramolecular force. So these are all, again, covalent bonds are intramolecular. But in this chapter, we're interested in intermolecular. And inter is a prefix that means between. If you interact, that means there's this something between you and someone else. You shouldn't be interacting with other people right now. If you have an intermission or an interlude, or if you interrupt, again, that always just means between. So intermolecular forces are forces, this shown right here, that are between molecules. Now, they are very, very different. So, for example, if you want to boil water, then to boil water, you have to completely separate the molecules. You are not breaking intramolecular forces, you're only breaking intermolecular. So, it only takes about 41 kilojoules of energy to boil or vaporize water. That is the energy to separate molecules from each other. But if you wanted to completely break every hydrogen and oxygen apart from each other, to break the covalent bonds, it's 930. And so you can see there's a much greater a degree of energy if you want to break covalent bonds. So when you boil water, you're not touching covalent bonds, you're only separating them. So again, it's like, imagine you're holding hands in hands with someone else, and I walk up to you and say, hey, that's not quarantining and isolation, social distancing. Well, what's going to be easier for me to do? Separate your hands from that other person, or tearing your entire arm off? So separating your hands is much easier. So that's just breaking this interaction between separate particles. But to actually, well, tear off an arm or tear off a hydrogen, that takes a lot more energy. And so notice again, a much greater amount of energy needing for that to happen. So you'll generally see intermolecular forces are much, much weaker than intramolecular forces. So covalent bonds that we've already talked about are stronger than these forces that we're going to be looking at today. Now, going back to breaking arms off versus just separating your hands, if I were to try to put your arm back on after ripping it violently off, and then I say, sorry, maybe that was a tad much, how easily could I put it back on? And you might say, well, that's pretty difficult. It's not going to just reattach like Velcro. But what about if I separated your hands, and then as soon as I left you, you just like holding hands, so you grab hold of each other again. So intermolecular forces are much more reversible. So they're more easily broken apart, but they can also reform much easier. So again, this allows them to shuffle around. So they're kind of sticky towards each other, but they can be easily separated and then recombined. So there's a whole lot more in freedom of interaction. But with the covalent bonds, intramolecular, you're not going to see a hydrogen and oxygen breaking apart and coming together, breaking apart, coming together, like you will these intermolecular forces. So When I say these forces are weak, I do want you to keep in mind Velcro. When it comes to Velcro, you probably know that Velcro, you don't think of it as a very strong interaction. Like you can easily pull Velcro apart. But the way Velcro works is you have these microscopic, maybe it's not micro, it's more like milloscopic, these really small plastic hooks and loops. And when you put them together, they hold. Now, to break a single hook and loop, it takes very, 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 very little energy. But what if you start grouping them together, hundreds, thousands, tens of thousands? Well, then Velcro can be very strong. You can probably show that or know that if you want to break Velcro, you don't pull the separate strands apart all at once because then you'd have to overcome all of them at the same time. Instead, you peel it. So you take just one end, and by just peeling on one end, you're having to break a much smaller number of Velcro hooks and loops at one time. If you try to pull the two separate strands apart all at once, it'll be much, 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 much more difficult. So this is the idea with intermolecular forces. Each one independently are really weak, but when you have a significant amount of them, their forces add up. So probably the best way we are going to be able to quantitatively measure intermolecular forces are phase change. Anytime you boil a molecule or melt it, you are having to put in energy to break those intermolecular forces. So the stronger the intermolecular force, the strongly they hold on to each other, it's going to mean that there's a higher melting or boiling temperature before it's going to separate. So something like water, water has very strong intermolecular forces. And we know this because you have to get it up to 100 degrees Celsius, which is pretty hot, before it will vaporize. But take helium. Helium, it only has to be at negative 452 Fahrenheit. That's just above absolute zero. So that very, 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 very low boiling point tells us it has super weak intermolecular forces. And we're going to talk about, so again, why are the intermolecular forces of helium so much weaker than something like water? Now, I put a couple review slides. Now, we just took a test over this, so this should be pretty fresh material, so I'm not going to cover in great detail, but I included it just so if you didn't get it in Unit 9, so you don't have to go back to a whole different set of notes, but it's going to be important to be able to say and characterize, is this molecule polar or not? Because if it's polar, it acts like it has a partial charge, partial positive, partial negative. And again, you get a polar bond with a difference in electronegativity. So a less electronegative atom like hydrogen, a more electronegative atom like fluorine. Fluorine is a little bit more selfish. It's going to pull electron density towards itself away from the hydrogen. So that gives us a polar bond. So then the only other part to remember is we also have to look at all of the bonds and their symmetry. So with ammonia, all the dipole moments are pushing electron density towards the nitrogen, making it polar. But here we have NF3 with all the dipole moments going in pretty much different directions. It's much, much less polar. That value of 0.24 is pretty close to zero. So if it has polar bonds, but the electrons are pulled in opposite directions, they cancel out. So again, we're looking for not just polar bonds, but how symmetric it is. And again, here's some things we could talk about varying polarity. Again, fluorine's the most electronegative atom, but if it's bonded to itself, it's nonpolar. It takes a difference in electronegativity. Again, looking at these four substances with one polar bond or two or three or four, the one with a single polar bond is more polar than having two or three or four. So because of symmetry, this one's completely non-polar when electrons are distributed across the entire thing. So again, keep this in mind because the first type of intermolecular force is called a dipole-dipole force. And if I were to say say, hey, what types of things have a dipole? It is polar molecules. So this term generally tells you it's a polar molecule which has a permanent dipole moment attracted to another polar molecule. So these hot dog looking things represent a partial positive and partial negative. So overall, it has a net charge of 0, but because there's more electron density on this half, it can have an attraction to a partial positive on another molecule, which has on the other side this repeating factor. And so when things are polar, you get these partial charges attracting and attracting and attracting. Again, so here's something like hydrogen chloride. HCl is polar, and so it has these, we call these dipole-dipole forces. So polar molecule with polar molecule makes for a dipole-dipole interaction. So it is an attractive force that would increase things like boiling temperature. So take these examples, fluoromethane versus carbon tetrafluoride, 1 polar bond, 4 polar bonds. If we go and look up their boiling point, we'll find that the one above has a higher boiling point by about 50 degrees, and it's because it is polar. This one, being nonpolar, does not have dipole-dipole interactions. So the more polar something is, the greater the greater the boiling point, because it has these attractive forces that higher temperatures are required to break these bonds. Again, there are some other factors that come into play when it comes to boiling and melting temperatures, like size and branching, or how well they can stack up. But polarity is the first thing I want you to know, that greater the polarity, the greater the boiling point. The second is called the ion-dipole force. So if dipole and dipole forces were between two polar things, a ion dipole is between something charged, an ion, and something polar. And so sodium ion is positive. It will have an electrostatic attraction towards the partial negative of something polar. But iodide, which is negative, will have a attraction towards the partial positive. So ion dipole is between a charge and something polar. Just to mention, this is the only type of force where you have to have a mixture. So you have to have an ionic compound like potassium chloride and then something else polar, like in this case acetone. So here acetone is polar. There's electron density being pulled to this oxygen. So there's a partial negative charge over here and a partial positive over there. So if you mix acetone and KCl, since potassium is positive, it'll interact favorably with the oxygen. Since chloride is negative, it'll interact favorably with the partial positive. And so if you try to dissolve potassium chloride in acetone, you'll find it will, because it has these ion dipole forces, and these are, again, favorable interactions. Now, definitely the most common seen example of an ion dipole force is hydration, and that is simply dissolving something in water. We said water is the universal solvent because we'll talk more about dissolving other molecules, but water can dissolve most ionic compounds because it forms these hydration shells. So again, here's table salt being broken apart. We've talked last semester about how they dissociate. Actually, that was this semester. And so what you'll find is the partial negative on the oxygen will surround the positive ions, and the hydrogen, which are partially positive, will surround the negative. And we have the partial positive for hydrogen can interact favorably with the negative of the chloride. So again, it's the different, these are ion dipole forces. So know that when you dissolve an ionic compound in water, it forms these hydration shells that have ion dipole forces. So it's still technically opposites attracting, except instead of a positive and negative, it's a positive and partial negative, or negative and partial positive. The third type we have is the London dispersion force. Now, instead of having a permanent dipole like water, or something that's polar, it's said to have a temporary dipole. And when we say temporary, it means fleeting, that it is not always polar. So here's just some generic particle that is nonpolar. There is no measurable dipole moment. But what we find is that even when things aren't polar, since electrons, that they are not set, they are not that they are delocalized. They're in their fleeting electron clouds. They are able to move about, and if you have something that comes near it that is charged or polar, it can induce a dipole moment. See this word induce. So it can induce a temporary dipole. So you put something charged next to this, it will cause the electrons to temporarily shift towards it or away from it. And so if you do this, you have a induced dipole moment, which is, these are very, very weak forces, but they still will hold these particles together. So again, this is called a London dispersion force, or you might hear or just see LDF. So these are notably for when you have non-polar substances. So if things are non-polar, they don't have the same strong interaction of polar or ion dipole, but at the very least, we say they have London dispersion forces. So here we're looking at induced dipole, but you can also have instantaneous. Now, the whole idea here is if you were to take a picture of a molecule that's nonpolar, if you could take a picture of its electron density in any given femtosecond, so like 10 to the negative 15 seconds, so, and then from one to another, you would find that there is a super tiny dipole moment. But, and this is just again, we could talk about the Heisenberg uncertainty principle, that these electrons do not have absolute position. They have highly favored positions, but they're not, again, they are not fixed. So since the electrons are able to move about in any given moment or instant, they possess a super tiny dipole moment. Now, if you go from 1 nanosecond to the next, to the next, to the next, you'll find, oh, they change. And on average, these things are completely nonpolar. However, because they still possess these super fleeting, very quick, momentary dipole moments, it is still an attractive force. So that's why something like neon, and I mentioned helium, you can condense these things to liquids. You just might have to get them down to like 20 Kelvin. I think neon has a boiling point of 25 Kelvin. So that's just, so if you want these super weak London dispersion forces to pull them together, you have to get lower than 25 Kelvin. And for helium, it's 4 Kelvin. So even though they're not polar, this is showing very, very weak, fleeting, instantaneous dipole moments. So these LDFs, they're weak, but there are a couple things that affect just how strong they can act. And so we call that ability to be polarized polarizability. So how easily can these electrons be distributed? And so probably the most important factor is how many electrons there are. If an atom only has one electron, whether it's shifted to one side or another of the atom, that's not very, you wouldn't call that very polarized. But if you look down the noble gases, helium has 2 electrons, neon has 10, argon 18, krypton 36, and so on. The more electrons there are, the more they're able to be polarized. And so that will lead to greater strengths in LDFs, which is why if you look at the boiling points of the noble gases, even though they're all nonpolar, the boiling points get higher as you go down the periodic table. So helium boils at 4 Kelvin, neon 27, argon 84, krypton 116, xenon 160, radon 202. So those are all very low temperatures, but still we see that as the number of electrons go up, then so does the boiling point. The other factor has to do with something we talked about called resonance. So if you have a resonance structure, the electrons exist in a more delocalized state, which also allows them to be more polarizable. Now, that's not something I'll probably have you actually quiz it or test it over. The more important one is the number of electrons. So if you look at these 5 molecules, all 5 of them are completely nonpolar. They're tetrahedral. But so then if you look at their melting points, it increases not because polarity is going up, but because the number of electrons is going up. So an easy way to figure, you don't actually have to count the number of electrons. Generally, as the molar mass goes up, so as you get to bigger and bigger substances, there's more and more electrons. So London dispersion forces go up as the molar mass goes up. So you'll see some questions in the homework that say like, hey, why does CBr4 have a higher boiling temperature or melting temperature than CF4? They're both nonpolar, and you would say it has a greater polarizability with more electrons to be shifted from one side to another. We can see this with the first 10 linear organic compounds. So here's methane, ethane, propane, butane. All of them naturally are found as a gas with 1 carbon or 2 carbons or 3 or 4. So as the number of carbons go up, we also see the melting and boiling temperatures going up. So again, these first 4, we see these temperatures increasing as the size of the atoms get bigger. Then when you get to 5 carbons, 5, 6, 7, and 8, from pentane to octane, and so on, nonane and decane, then we're continually, these are now liquids, so the forces are now strong enough to keep them condensed to the liquid state. But then as, again, you add more and more and more electrons, the boiling point and melting temperatures go up. Now, when you finally get up to 18, this is when you'll finally start to get molecules into the solid phase. Again, here you can see a melting point of 28 degrees. So if you think of something like a candle, candles are made of paraffin wax. They have molecules that look very similar to this. And so because it's a solid, you can know that, well, even though it's nonpolar, like candles don't dissolve in water because they're nonpolar, but they're solid because the size of the molecules are just really, really big. So while polarity makes boiling points go melting and boiling points go up, the other factor is size, and that's because with more electrons, they're more polarizable. So to finish up, here's a few questions of what type of force would you find between these particles? So the first question you need to ask yourself, are they polar? So this is something you need to know from last chapter, and bromine is more electronegative than hydrogen. It is polar. Sulfur is more electronegative than hydrogen. It has a bent configuration, making it polar. And so if you have 2 polar things, it is a dipole-dipole attraction. Carbon tetrachloride. As opposed to a mixture, we're just saying, what if you have liquid CCl4? What would be holding it together? So this thing is nonpolar. It's got polar bonds, but again, from unit 9, if you know it's tetrahedral and all the dipole moments cancel out, then it's nonpolar. And the go-to answer for if it's nonpolar is always going to be the London dispersion force. So it has instantaneous dipole moments that can hold it together. Now, again, we say they're relatively weak, but it still has a higher boiling point of 76 degrees Celsius, but that's because of its size. CCl4 has a whole bunch of electrons. So again, water boils at 100, so it's not as high as water, but this thing weighs almost 10 times as much as water. So even though it's almost 10 times bigger, it's lacking polarity, it still has a lower boiling point. Here we have iodine and sodium. So here's something charged, and then here is something nonpolar. So this would be a ion-induced dipole moment, which falls under the category of London dispersion force. Here we have formaldehyde, so you would need to draw out a Lewis structure, but you would find it's polar, and then here is an ionic compound. So if you have polar and ionic, it is called a ion-dipole force. Here you have ammonia and benzene. This is polar, this is nonpolar. This is a dipole-induced dipole force, which again is just categorized as London dispersion. So all of these, oh, and there's that. The next slide, oh, that's kind of redundant, but yeah, there's that. Okay, so that's going to be it for today. Tomorrow, and by tomorrow I mean Monday, I'll post a video about the next and probably most significant intermolecular force called the hydrogen bond. So there'll be 4 in total. So there's the London dispersion force, the ion-dipole force, the dipole-dipole, but then the most significant is the hydrogen bond. It is by far the strongest, and so if a chemical can make a hydrogen bond, its properties will be quite different from if it does not. Anyway, have a hopefully super fantastic day, and I will see you, I don't know, sometime. Maybe never, or eventually.